Hello everybody, this is my lecture for week 11 session 2. We completed chapter 6, the second law of thermodynamics. In this chapter we discussed the second law of thermodynamics. Also you learn uh, three cycles, the refrigeration cycle, heat pump and heat engines, and then we discussed the Carnot cycle. So as a quick review of my previous lecture, we discussed the Carnot cycle. Carnot cycle is totally reversible cycle. It has four actually steps or four processes. It has two adiabatic process and two isothermal or constant temperature processes. So here you can see actually the heat engine that work based on the based on the Carnot cycle is called the Carnot heat engine. Is totally reversible. Here you can see the PNU diagram for the Carnot heat engine cycle. This is the first step, and then evaporator actually absorb heat from a heat source at constant temperature, and then this is the turbine step. So here actually W actually net produce, and then this is at constant actually adiabatic process with Q equals to the 0. The third step is the um, actually condenser, and then in this step actually heat is rejected at constant temperature to the source, and then the last to the sink, and then the last one is actually the pump, and then fluid is returned to the boiler at actually during an adiabatic process. So this is totally reversible process, and if this process is reversed, we will have the Carnot refrigeration or heat pump, cycle. We discussed it, um, on Monday. So to calculate the actually thermal efficiency of any heat engine, you have two options. For the irreversible heat engines, you can use this equation to find the thermal efficiency, or you can use the definition of actually thermal efficiency. The definition is the desired output over required input. For the reversible process, you have two options. You can either use this equation, or you can use the definition of, actually you can substitute this QL over QH with absolute temperature with the TL over TH. So you have two options for the to calculate the efficiency, thermal efficiency of reversible heat engines or Carnot heat engine. You can either use this equation or this one. Also, guys, you can use the definition for the thermal efficiency based on the definition of thermal efficiency, the desired output over required input. So keep in your mind that, guys, what you can do, you can calculate the thermal efficiency of the given system. For example, you have this heat engine, you can calculate the efficiency of that given heat engine, and then you can compare it with the Carnot heat engine. If the efficiency, the thermal efficiency of given system is lower than the thermal efficiency of the reversible heat engine, then your given system, your given heat engine is a irreversible heat engine. If the thermal efficiency of the given heat engine equals to the thermal efficiency of the actually Carnot heat engine, then your heat engine is a reversible one. And if your thermal efficiency, if given the thermal efficiency of given actually heat engine is higher than the thermal efficiency of Carnot heat engine, then it's impossible. It's impossible, guys, to actually make this heat engine. Keep in your mind that in these equations all temperatures are absolute temperature. You need to use Rankine or um, let's say you need to use Rankine or Kelvin temperature here. So for the refrigerator and heat pump, you need to use the COP. So you have again two options for the irreversible process. We discussed it, in previous lectures. You can use either this equation or this one for the refrigerator or heat pump. Keep in your mind that, guys, in addition to these two equations, you can use the definition for the efficiency. You can just write the COP equals to the desired output over required input. Keep in your mind that the desired output for the refrigerator is actually QL, and for the heat pump, the desired actually output is QH. So you can also use, that definitions to calculate the COP of a reversible refrigerator and heat pump. For the reversible one, guys, you have two options. You can use either these equations, or you can substitute for the QH over QL with TH over TL, or in this equation you can substitute the QL over QH with the TL over TH. Again, guys, keep in your mind that in all this equation you must use the absolute temperature. And then again, guys, you can calculate the COP of a given refrigerator or heat pump, and then you can compare it with the COP of reversible heat engine and heat pump and refrigerator, and then make a decision if possible to have this refrigerator or heat pump, or it's impossible. So this is a short review, guys, from my previous lectures. Let's go over 3 examples today. The first one, an inventor claimed to have developed a refrigerator that maintained the refrigerator space at 40 Fahrenheit while operating in a room where the temperature is 85, and the COP of this actually refrigerator is 13.5. Is this claim reasonable? Okay, guys. To solve problem, guys, in chapter 6, 7, and 9, I highly recommend you to draw a simple schematic. Why? Because in this chapter, guys, you are dealing with more than one, equipment. Look, in chapter, for example, 5, you just work on, let's say, for example, heat exchanger. You work on, let's say, for example, mixing chambers. Correct? So it's really easy to just memorize all information. But in this chapter, guys, we are dealing with a cycle, and then you have more than one equipment. So I highly recommend you to just draw a simple schematic, and then add all available information to that schematic. This is much easier to solve problem. Okay, so here we have a refrigerator, and then you have actually 2 temperature for the sink and source. So this is a simple schematic, guys. We have the refrigerator, and then we have 2 actually heat sink and heat source. So we have the temperatures, and then you are asked about this actually claim. Now what you need to do, guys, you need to calculate the maximum actually COP of this refrigerator. Correct? And then compare the COP of max with this value, and then make a decision based on the COP max and then the COP this value. So to calculate the COP max actually is for reversible refrigerator, or for the Carnot refrigerator. So based on my previous slide, you can write the COP for the refrigerator. You have actually 2 options. You can write it based on the TH over TL, or you can write it based on the QH over QL. Here, guys, you have the temperatures, correct? So you should use this equation to find the COP of max, or the COP for the reversible refrigerator. So it's easy, guys. You have everything. You can simply calculate the COP max. But before you calculate the COP max, guys, you need to convert this temperature to the absolute one. This is really, guys, important. Don't substitute 85 over 40. This is incorrect. You need to convert this Fahrenheit temperature to the Rankine. So I just convert these values to the Rankine. Please spend 2 minutes. Please pause this video, spend 2 minutes, and then calculate the COP for the reversible, a refrigerator. Okay, so if you substitute this value, the COP max will be 11.1, and then you can make a decision, guys. You have the COP for the given refrigerator, you have the COP max, And then based on these values, guys, the COP for the refrigerator is 13.5. The COP for the reversible one is 11.1. And this value is higher than this, reversible value. So it's impossible, guys, to just make this, refrigerator. And then the claim is not valid. Okay, this is the first one. The second one, guys, for the second one, there is a heat pump, and then this heat pump receive heat from a lake. So we have the temperature of this lake is 6 degrees centigrade, and then it just supply heat into the house with the temperature of 23. Here, guys, we are lucky we have, the schematic of this, problem. However, if you don't have anything, guys, you can just simply draw the schematic. Look, there is a house, there is a heat pump, and then there is a, lake. You have the temperature for the lake, and you have the temperature for the house. Sorry. Keep in your mind that this house and lake, can work as, a heat source and heat sink. Now, also, guys, for the first step, we know that the heat loss is 52,000 kilojoule per hour. And you're asked to determine the minimum power supply to the heat pump. Okay, guys. So, as the first step, before actually, the first step, look, guys, you have the Q dot loss, correct? The Q dot loss is given. Now, if the temperature of this house is constant, correct? If we have a steady state temperature or a steady state conditions, for this house, then the Q dot H to this, house must be equal to the Q dot loss, correct? Otherwise, what happened? Otherwise, the temperature of this house increases or decreases depending on the relationship between these two Q dot. So, in this actually problem, you can assume that the Q dot loss equals to the Q dot H. Why? Because the temperature of this house is constant. This is the first actually, hint to solve this problem. The second one, guys, just transfer all, available information to this, schematic. So you have the T dot H is given, you have the T dot L, and then you just need to convert this temperature to the absolute values. And also you have the Q dot L, and now you know that the Q dot L equals to the Q dot H. Okay, guys, please open, the PDF file that I share on the Blackboard. And yeah, so this is the different steps, guys, to solve, this problem. The process schematics available. So add noun parameters to the process schematic. So you just need to add, the available information. The third step, guys, you need to find the W dot in, the first unknown parameter. To find the W dot in, guys, you need to select a control volume, correct? And then find the W dot in. What is the best control volume, guys? Look, you have several options to actually as a control volume. You can select this house as the control volume. You can select heat pump. You can select the heat exchanger. You can select the lake, or you can select the whole actually system as a control volume. But the best control volume is the control volume that you have some information about that control volume. This is the first criteria. And the second one, the unknown parameter must cross the boundaries of, control volume. For example, if you select the house as a control volume, correct? You have the Q dot H. That's good. But this actual, W dot in doesn't cross, the boundaries of your control volume. So it's not a good control volume. So based on my explanation, guys, please spend 2 minutes and then answer this question. What is the best control volume for this, to actually find the W dot in? Please pause this video and then answer this question. Okay, guys, based on my explanation, I think the best control volume to find the W dot in is this, heat actually pump. If you select this heat pump as a control volume, because the W dot in cross the boundaries, and also you have the Q dot H, correct? Now, if you select the heat pump as the, control volume, Please list all actually available equations that you can use to find the W dot in. I already did, guys. You have three equations to find, the actually W dot in. The first one is the COP for, irreversible, actually, uh, heat pump, correct? Based on the definition of COP, the COP is the desired output, which is the Q dot H over required input, which is W dot in. The third equation, guys, is the same as the first equation, but the difference between the first and the third equation is that I wrote the COP max. The COP max is for the reversible heat pump, correct? So if you just rewrite this equation for the reversible one, you will get the maximum COP. So at constant Q dot H, guys, you will have the COP max when the W dot into the actually heat pump is minimum, correct? By having the minimum W dot in, you will have the COP max or the COP for reversible heat engine. And then the second heating equation is the COP max for reversible actually heat engine based on the TL and TH. I just explained, this equation in my previous slides. Now you have all these three equations, guys. Again, the first one is for the irreversible heat engine. The second and the third one is for the reversible one. Why I wrote for the reversible one? Because we are looking for the W dot in, and we will have the W dot in mean when we have the maximum COP or we have the reversible, heat pump. Okay, please spend 2 minutes, guys, and then answer this question. Which equation is the best one to find the W dot in mean, for this problem? Please pause this video and then answer this question. Okay, guys. So, yeah, to find actually the W dot in, the W dot mean, you need to use the third equation, correct? Because we have the W dot mean in this equation. But in this equation, Q dot H is known. So what you need to do, you need to find the COP max for the reversible process. This is unknown. How you can find this value? You can use equation 2 to find the COP max, and then you can substitute into this equation to find the W dot mean. Please spend 5 minutes and then just solve, equation 3 and equation 2 to find the W dot mean. Please pause this video and then find the W dot mean. Okay, guys. So, yeah, here, I just select the heat pump as the control volume, and then these are the equation that I explained. So what you need to do, if you substitute for the TL and the TH into this equation, you can find the COP max, which is 17.41. And then if you substitute this COP max into this equation, you can find the W dot mean, which is 0.83 kilowatt. Okay, the second part. To find the second part, so actually the second part, you are asked to find the minimum mass flow rate of the lake water, correct? So you have the schematic of this process. Please spend 2 minutes, pause this video, and then just transfer all available information, to this, flow chart for the part B. Okay, guys. The only available information for this one is the delta T. So you know that the delta T for the water here is 5 degrees centigrade. So meaning that if the inlet of the water into this, heat exchanger is 6 degrees centigrade, the exit is 11, correct? The lake exit water here. So this is the only thing. You have the delta T. Now, the second step, you need to select a control volume to find the M dot for water. Based on my explanation for the previous, section, please spend 2 minutes and then pick the best control volume to find the M dot. Please pause this video and then select the best control volume. Okay, guys. So based on my explanation, you are looking for the M dot for water. So you should select this actually heat exchanger as a control volume. Why? Because actually this actually unknown parameter, the M dot, must cross the boundaries, correct? If you select this heat exchanger as a control volume, this actually M dot cross the boundaries. So heat exchanger is the best one, correct? Now please spend 2 minutes and then just list the equations that you can use to find the M dot for water based on this control volume. Okay, guys. So look, for the second part, I just add the information, available information. I just pick the heat exchanger as a control volume. What is the energy balance for the heat exchanger? If you remember, for the heat exchanger, you can write Q dot in for the cold fluid equals the Q dot H from the hot fluid, correct? Or you can write Q dot in equals the Q dot out, correct? This is the basic equation for the to design a heat exchanger. Q dot H equals the Q dot C, or you can write Q dot in equals to the Q dot out. What is the Q dot in to this heat exchanger, guys? The Q dot into this heat exchanger is M dot for the water times Cp for the water times delta T. This is the Q dot in. What is the Q dot H from this heat exchanger? The Q dot the Q dot out from this heat exchanger is Q dot L. If you combine these two equations, I mean for the Q dot in and Q dot L out, you can write M dot Cp delta T for the water equals to the Q dot L, from this, heat exchanger, correct? So look, guys, you are looking for the M dot for water. The Cp of water is known. You can find it from the tables. The delta T is given, 5. So to find the M dot, guys, you need to find the Q dot L. Question: how you can find this Q dot L? Please spend 2 minutes and then answer this question. How you can find the Q dot L? Please pause this video and then try to find the Q dot L. Okay, guys. If you select the heat pump as a control volume and then you write the energy balance for the heat pump, you can find the Q dot L. How? Look, guys, what's the energy balance for the heat pump? The energy balance for the heat pump actually is a cycle. You can write W dot net equals the Q dot net, correct? This is the energy balance. What is the Q dot net? Q dot net is Q dot in minus Q dot out, or Q dot L minus Q dot H. This is the Q dot net. What is the W dot net? W dot net is W dot out, which is 0, minus W dot in. So the W dot net is actually negative W dot in. If you substitute this thing here, you can write Q dot L equals to the Q dot H minus W dot in. You have the W dot H, sorry, you have the Q dot H, you determined from the previous section. You have the W dot in, and then you can simplify the Q dot L. Please use this energy balance equation and then find the Q dot L and then substitute here to find the M dot for water. Please spend 2 minutes, pause this video, and then calculate the M dot for water. Okay, guys. So look, I just substitute for the Q dot L and Q dot H into this equation, and then this is the Q dot L. So if you substitute this Q dot L into this equation, you can find the M dot for water. Now, question: you are asked to find the M dot mean, the minimum actually water mass flow rate. So is it the minimum value? Yes. Why this is the minimum value? To answer this question, we need to go back to this, equation. Look, guys, into this equation, you substitute the W dot in mean. Sorry, let's go back to see if you are asked to find the W dot max or mean. Yeah, the minimum max, right? Okay. So, look, guys, here you have actually the W dot in mean, correct? We calculate the W mean, in the previous section. So if you substitute the W dot mean here, this actually QL will be the minimum QL, correct? Minimum Q dot L. If you substitute the minimum QL into this equation, this M dot will be minimum. Yeah, yes, this is the minimum M dot. Again, guys, this is the procedure to solve problems in this chapter 7 and chapter 9, because you are dealing with more than one equipment, you are dealing with a cycle. I recommend you to draw a schematic of the process. This is the first step. The second step, please add all available information to that schematic. The third step, try to just select the best control volume, and then you should use equations for thermal efficiency, for COP, for reversible irreversible process, and then you need to combine these equations with the energy and mass balance equations that you learned in previous chapters to solve the problems. Okay, and then this is my last problem for today. So we have two Carnot heat engines. So they are Carnot heat engines. They are reversible one, and then they work in series. So the first one receives heat from the reservoir at 1400 Kelvin and reject waste to the another reservoir at T, and then the second one receive heat from this actual reservoir and then reject heat to the third actual reservoir at 300 Kelvin. So you know that the thermal efficiencies of both heat engines are the same. Determine the temperature T. What is the temperature? This temperature here. Again, guys, the first step, you need to just draw a simple schematic. So we have two Carnot heat engines, and then we have three actually reservoirs. Look, guys, this is the heat engine one, works between the TH and T. The second one works between the T and the TL. So temperature must be in absolute temperature. You have the absolute temperature, you're good. And then you need to use the definition for the thermal efficiency. So if you use the definition for the thermal efficiency for the first heat engine, you can write the thermal efficiency of the first heat engine equals to 1 minus, what is the TL for this heat engine? The TL for this heat engine is T, correct? Over TH. This is the first actually, thermal efficiency. The second one, if you want to write the thermal efficiency for the second one, you need to write 1 minus TL. What is the TL for the heat engine 2? It's actually the TL over TH. What is the TH for the second heat engine? The second heat engine, the TH is actually this T. And you know that the thermal efficiency of the first one equals to the second one. If you actually combine these three equations, you can simply write the temperature equals to the square root of TH times TL. You have the TH and TL, and then you can simply find the answer, which is 648. Okay, guys. This is my lecture for today. Please study, all these, three examples. Also, now you can solve, you can work on your assignment. I think assignment number 11 from this chapter. We completed this chapter. I just solved one more example on Friday, and then we start chapter 7. Thank you very much, guys, and have a great